In this video, we'll cover the very basic concepts of digital logic circuits. Although digital logic circuit is designated as the prerequisite of the computer architecture class, many of the students may not have the chance to take digital logic circuits before taking computer architecture class. So I will cover the very basic concepts that is a small part of the digital logic circuit design class that are required to take the computer architecture class. The first table shows the AND operation. It takes two Boolean values, x and y, and since each input can be either zeros or 1, all possible combinations are 4 combinations. The result of the AND operation is 1 only when both inputs are 1, and the output is 0 for all the other cases. It's simple, right? The symbol below the table is representing a hardware component that performs such operation in a digital logic circuit. Such component is called a gate. I guess you can easily understand how other operators such as OR or NOT operator work. Let's look at the NAND operators for this time. NAND represents NOT AND operator. So it's basically inverts the output of AND gate to opposite value. So the output of AND gate is 1 for all the combinations except for 1, 1, which is 1 becomes 1 for AND gate. But for NAND gate, the output of an AND gate is all 1 for other combinations except for the case when both inputs becomes 1. In that case, the output becomes 0 for an AND gate. So it's exactly opposite of the AND gate. I guess most of the students are familiar with the digital versus analog systems. In digital systems, we represent information using ones and zeros, and we also process or compute such information using semiconductor hardware that processes such ones and zeros. In a digital system, we distinguish these values as ones and zeros, or true or false. Sometimes we use ones and zeros, or sometimes we just call these as true or false values. They are essentially the same. These ones and zeros are actually electrical signals in the hardware, and a voltage level above a certain threshold is regarded as ones, and a voltage level below a certain threshold is considered as 0. The voltage level that divides the ones and zeros can be different for different components in a computer system. For example, inside a CPU, the voltage level is almost close to the 1 volt to reduce the overall power consumption. However, when the data or information is delivered out to the outside world, we may need a higher voltage to reliably transfer the information. So voltage level that represents 1 is called VDD, and voltage level that represents 0 is called ground or GND. Processing information using these ones and zeros is based on Boolean algebra. The basic operators in Boolean algebra is very simple. The tables shown here is called truth tables. It lists the possible inputs and outputs for Boolean operator, and it also shows the corresponding output value for each of the input combination. The symbol of the NAND gate also represents such behavior. So it's basically the same as the AND gate, but it has a small circle or bubble at the output. These bubbles usually means an inverted operation in a digital logic circuit. So it's an AND gate, but its output is inverted. By connecting these basic logic gates, we can construct a logic circuit that performs the desired operation. This example, which we'll study later, represents a circuit that performs add operation. It adds A and B plus carry in, and then it outputs sum of A, B, and then it also outputs the carry out that goes to the next bit. Let's briefly look at how these gates are made. In this simple circuit, we have a power source, such as battery, and a bulb. Let's imagine you have a switch that connects or disconnects the circuit given the input. This switch becomes connected when input to the switch is 1, and it disconnects the circuit when input to the circuit is 0. You can easily imagine when we give 0 to input to the switch, we can turn off the bulb, and if we give 1 as the input to the gate, then we can turn on the bulb. Simple, right? And suppose you have two switches in series. To turn the bulb on, we have to connect both switches. That means we have to give 1 and 1 to A and B respectively. That means only we have 1 at both inputs, we can turn on the output of the circuit, and if either of the inputs becomes 0, then the output of the circuit becomes 0 or turned off. This operation is actually how an AND operation works, right? Let's look at the below case. So we have, in this case, we have two switches in parallel. And in this case, we can connect only one of the circuits. One of these paths is enough to turn on the output. So even if we have one at the only one of the inputs, we can still turn on the output. And it's okay to have both ones and connect two paths simultaneously, and we can still turn on the output. And then only when we have 0 and 0 at both inputs, the circuit is completely disconnected and the output becomes 0. So this resembles the operation of an OR logic gate. The actual semiconductor circuits are a little more complex than the combination of switches. A transistor in semiconductor circuits is similar to switches that we just described, but the one difference in semiconductor transistors is that in the previous switch example, the bulb turns off when the bulb is disconnected from the power source or VDD. But when we are using semiconductor transistors as switches, disconnecting the output from the power source or VDD is just not enough to turn off the output. When we are creating a logic circuit using semiconductor transistors, then we have to explicitly connect the output or bulb to the ground to completely turn it off. Some of you may. So in this case, we have, when we are turning on the circuit, we connect the bulb to the power source and disconnect from the ground. And when we are turning off the bulb, then we disconnect from the power source and we connect to the ground. So we have to have a pair of paths that either connect to the power source to turn the output on or make the output value to 1 or true, or we have another path that connects the output to the ground when we want to put 0 to the output. Some of you may already heard about NMOS or PMOS devices in CMOS circuits. Since the focus of our lecture is not about studying the transistor devices itself, we will not get into the details of these CMOS transistors and how they work and the physics behind the transistor devices. For now, you can just think these NMOS or PMOS transistors as just switches that we just described. One thing you have to remember is that the NMOS transistors and PMOS transistors are slightly different, and I'll explain the difference. The NMOS transistor connects the source, connects the source and drain when the input to the gate is 1. And it disconnects source and drain and when input is to the gate is 0. We use these NMOS transistors to connect the ground to the output to make the output 0. On the contrary, the PMOS transistors are used when we are connecting the output to the source power source or VDD. That means we are using PMOS transistors to make the output 1. And like we just explained before, we need a pair of paths to make the output to either 1 or 0. So remember that PMOS device is used when to make the output to 1, and NMOS transistors are used to make when we are to make the output 0. Another difference between PMOS and NMOS devices is that PMOS transistor connects the source and drain when the input to the gate is 0. So when we give input 0, the PMOS transistor connects source to the drain, and drain, we can think drain as the output of the circuit. And when we give 1 to the gate, then source and drain becomes disconnected. So if you're confused about the difference between NMOS and CMOS, NMOS and PMOS, you can look at this symbol. So we have a small bubble to the input to the gate, right? And when we are explaining a NAND gate, the small bubble at the output of NAND gate inverts the output of the NAND gate inverts the output of the AND gate to become NAND gate, right? And the similar operation, similar rule applies here. For NMOS devices, input of 1 connects source and drain, but PMOS devices, input of 0 connects source and drain, and we can relate those inverted operation by looking at this small bubble at the gate symbol. So let's look at how we can construct an inverter gate or NOT gate using a pair of PMOS and an NMOS device. So here we have 2 transistors, one PMOS and one NMOS, and this side is input to the inverter gate, and this side is output from the inverter gate. And here we have a PMOS gate, a PMOS transistor, and this side is the source of the PMOS gate, and as we described in the previous slide, the source of a PMOS transistor is the power source or VDD, and we have a gate that controls this transistor, and we have the drain of this transistor. And below we have an NMOS device, and the source of the NMOS device is here, and drain is this side. And the source of NMOS device is, as we described earlier, is connected to the ground. And this side is the input to this NMOS device, that the gate of this NMOS device. And this PMOS device and this NMOS device is connected to the same input, and their drain is connected together and becomes the output. So how this inverter gates operates using 2 examples. So Since it's an invert gate, we have only two cases of operation, when we are getting 1 as input and outputting 0 as the output, and when we are getting 0 as input and the output becomes 1. So when we have 1 as input, then what would happen to this PMOS side? Since we have 1 to the input to the PMOS side becomes disconnected, right? And for the NMOS side, since we have 1 in the NMOS gate, this NMOS gate becomes connected. So the source and drain of this NMOS device becomes connected. That means the output of this side is connected to the ground. So it's outputting 0 as the output. And this side is disconnected and has no impact to the output. Let's look at the opposite case. When we have 0 as the input, then the PMOS side becomes connected and the power source is connected to the output, and we get 1 as the output. And the NMOS side becomes disconnected and the ground does not affect the output of this inverter gate. So by connecting these PMOS and NMOS device and tying their drain together and giving them the same input to their gates, we can construct an inverter gate that negates the input as the output. So let's look at a little more complex case. In this case, we are showing the example of NAND gate. And as we discussed, the NAND gate is the inverted AND gate. So we have 1 when we have 0, 0, or 0, 1, or 1, 0, and our output becomes 0 only when we have 1s in both X and Y inputs. Here, the construction NAND gate is constructed by connecting two PMOS gates in parallel and two NMOS gates in series. So let's look at the case when we have zeros in both inputs. That means when we have 0 in X and 0 in Y, and output becomes 1. In this case, since we have 0 and 0 to the input of the PMOS gate, this one is disconnected and this one also disconnected, and this PMOS is connected and this PMOS becomes connected. That means the ground doesn't affect the output and the power source is connected to the output, so the output becomes 1. Let's say we have 0 and 1 in both inputs. Sorry, I use XY here and AB here. Anyway, so when we have 0 in A and 1 in B, this gate is connected. So the ground and this side becomes connected. But it cannot affect the output because this part, the PMOS at the NMOS gate for A input is disconnected because A is 0. So the ground is disconnected from the output, but the power source can be connected to the output because one of the paths that connects the power source to the output is connected because A is 0. It doesn't matter this side is disconnected because we have the path that connects the power source to the output, and the output can become 1. Only when we have 1s in both inputs, this part and this part connected, and both of these passes are disconnected, and the power source is disconnected from the output, and the ground is connected through these series of NMOS devices, and output becomes 0. So this is how we construct a NAND gate using a conflicting pair of PMOS devices and NMOS devices. And if we can connect 3 NMOS devices and 3 PMOS devices, then we may have 3 input NAND gate. So far we have discussed how we process ones and zeros in a digital system. But we are not just interested in dealing with zeros and one zeros or one ones. We want to process larger numbers. We want to process lots of data for machine learning or AIs or whatever, and we want to process colorful graphics, and we want to do various things. So how can you do that? So we want to process a valuable piece of information using combination of bits. So let's start by a very simple thing. How can you process integer numbers like 1, 2, 3, 4, 5, and 6, and so on and so forth? So when we are processing an integer, we are combining multiple bits of zeros and ones, and representing integer using those binary bits are called binary numbers. And you probably are familiar with these binary numbers in your middle school or high school studies, but let's go over this once again. So here we are representing an integer using 5 bits of zeros and ones. So we have 1 0 1 1 0, and as you can imagine, this one represents 0, and this one in this case is not just 1, but this 1 times 2 to the 1. Similarly, this one is not just 1, it's 1 times 2 to the 4. So each digit corresponds to 2 to the n or 2 to the I digits. By combining these bits, then we can have the actual number. So here 10110 is actually adding 2 to the 4, 2 to the 2, 2 to the 1. And this is 16, and this is 4, 2. So actual number that is represented by this one is 22 in decimal. So if we have n bits or n bit binary numbers, then we can represent one of the 2 to the n possible numbers. So for example, if we have 3-bit binary numbers, then we can represent one of the 2 to the 3 integers, or integers ranging from 0 to 7. In our computer architecture class, we'll basically study 32-bit computer systems. In 32-bit computer systems, each numbers are basically represented in 32 binary bits. So we can think this as a fixed slot of 32 binary bits, and almost in all cases, the numbers are represented using these 32 bits. Even if your number is small, like if you are dealing with like 3 or 4, you are still using these 32 bits of data or 32 bits in your hardware to represent a number. Since we are dealing with hardware, and hardware cannot be changed every time we are using different number. Even if we are using a number of 3 or 4, we just cannot use 3 or 2 bits of hardware. We still have to use 32 bits, and almost all bits are 0 except for last few bits that represent 3 or 4. Anyway, you will see lots of these samples while we are studying the computer architecture, and we are representing numbers in 32 bits. And here, this example shows 32-bit positive number of 1010 and zeros and 1010, and this is representing this number. And when we are dealing with 32-bit positive number or 32 bits of data, each of these bits are independent bits, and to represent each of these bits, we need separate electric signals. So we should have some kind of wire that conducts electrical signals to convey each of these bits in our hardware. But when we are drawing our circuit, or when we are drawing our computer architecture, drawing all 32 bits of wire that conveys or delivers this 32 bit can be cumbersome. So when we are drawing a line or wire that conveys 32 bits of data, we just simply draw a single wire and indicates that this wire actually contains 32 individual bits. And the notation for drawing a wire that contains n bits is like this one. So we have a small slash here and write the number of bits here. So instead of drawing all 32 bits individually, we can simply represent in this way. So small naming convention here, since we are dealing with groups of bits in our computer systems, we have to name those groups of bits in certain way. So each bit represents 0, 1, and when we have 8 bits, it's called byte. And when we have 16 bits, it's called a half word. And when we have 32 bits, which is the common data size when we are using a 32-bit computer, is called word. So when we have a group of bits that represents a number, then we have a bit that represents the smallest number. Like when we have this bit represents 2 to the 0, and this bit represents the largest number in our digit, and it represents 2 to the 31. So even if they are same zeros and ones, this bit represents the smallest number, and this bit represents the largest number in our group of bits. So when we have this group of bits, then the bit that represents the smallest digit or smallest number is called least significant bit, or LSB, and the bit represents the largest digit or largest number is called the most significant bit, or MSB. So, and we just described how the numbers are written in binary format, and we also know how to convert those binary formats into decimal number. And if you studied binary numbers in your middle school or high school, then you probably know how to convert decimal into binary numbers. And we know these binary numbers and decimal numbers because decimal is the number system that normal humans use, and the binary system is actually the numbers. It's the actual way the numbers are represented in hardware. But when we are studying computer architecture, sometimes it's convenient to represent numbers in hexadecimal format. Hexadecimal format is the base is 16. So decimal is base is 10 and binary is base 2, and hexadecimal is base 16. The reason why we want to express the numbers in hexadecimal is that 10 decimal numbers, the base of 10, is not a number that can be represented in 2 to the n. But 16 is 2 to the 4, right? So it's very easy to convert a binary number to hexadecimal number and vice versa. But converting a binary number to decimal number or decimal number to binary number can be done if you have a small piece of paper or calculator or whatever, but it's not instantaneous. But converting between hexadecimal number and binary numbers are very easy because 4 binary bits can be converted into 1 hexadecimal digit, and 1 hexadecimal digit can be converted into 4 binary bits. So if you have 32 bits of binary value, then it can be converted into 8 digit of hexadecimal values, and we can just convert each of digits of the hexadecimal number to binary number, or we can just convert each of these 4 binary bits into hexadecimal bits, right? So when we are dealing with the numbers in our computer system, then converting those numbers into decimal takes time, and converting decimal numbers into binary bits that will be represented in hardware, it also takes time. So we can just simply use hexadecimal numbers, which can just convert it by just by looking at those numbers. Okay, let's discuss the addition and overflow in binary numbers. So adding the numbers in binary format is very similar to adding the numbers in decimal format. Only we have two possible values in each digit. So if we add those 1 and 1, then we have 0 and 1 carry bit. And when we are adding 2 zeros and 1 carry bit, we have 1 here. So adding those two numbers are very easy, but you have to only remember that there are two possible numbers in each digit, 1 or 0, and adding two ones results in 1 0. So one thing you have to remember when we are dealing with additions in the digital logic circuit is that we are dealing with a fixed number of bits. Here we are adding two 8-bit numbers. So this one is 8-bit and the another operand is 8-bit, and result is also be another 8-bit result. However, depending on the input value, the result may go beyond the available number of bits. Here, this value is 10100, and this is actually 42 in decimal, and this one is 253 in decimal. And if we add these two numbers, then the result is 42 plus 295, and this cannot be represented by just using 8 bits. So, as you can see from the generated carry, the final carry goes beyond the 8-bit range, and it requires 9 bits to correctly represent this number. But if we just represent this value in 8 bits, this value is 10011. This is 39, which is clearly a wrong answer for adding these two numbers. Right, so this phenomenon that is getting incorrect result due to this limited number of bits is called overflow. So depending on the CPU type, there are numerous ways to deal with these overflow cases. In some cases, the CPU reports to the user that there was overflow happened, and the result may not be incorrect. Or in some cases, the CPU just ignores these overflow cases, and then just let the user to deal with such cases. Okay, let's move on to another topic in the number system issues. So far, what we have discussed is representing positive integer, 0 or positive integers using binary bit numbers. However, when we are saying integer numbers, we also have to represent the negative integer values. So how can you represent negative values using binary bits? So there are two possible ways. One of the ways, which is much easier to imagine, is using a special bit to represent the sign. The sign means the plus or minus. So when we have n bits, use n minus 1 bit to represent the actual magnitude or absolute value, and use just 1 bit to represent whether the number is positive or negative. For example, if the number is positive, then we can just use 0 as the sign bit, or we can use 1 to represent the number is a negative value. For example, if we have 4 bits to represent a number, then we can divide the 4 bit into two parts. 3-bit part, which is 4 minus 1 bit, equal 3-bit parts, as to represent the magnitude of the value or absolute value of the integer value, and use the MSB, the most significant bit, as to represent the sign bit. Though 101 is representing 5, 0101 is positive 5, and 1101 represents negative 5. So this is very intuitive, and we can easily decode which value this number represents by just looking at the sign bit and the absolute value or magnitude. So when we have this type of number representation, the possible range of possible number range that can be represented by using this system is from 2 to the n minus 1 minus 1 to 2 to the n minus 1 minus 1. So, for example, if we have 4 bits like this one, then the largest number that can be represented is 1 and 0, 1, 1, 1, which is plus 7. Plus 7 is 2 to the 3 minus 1. And the smallest value that can be represented using this system is 1111, which is representing minus 7. Minus 7, which is minus 2 to the 3 minus 1. And this one and this one. Okay, so what's the problem with this sign and magnitude number representation? So if we have this number representation, then it's a little bit tricky to perform additions between positive and negative numbers. So let's say if we want to perform this operation, 5 plus minus 5. This is actually 5 minus 5, right? But let's see what happens if we just add these two numbers. Plus 5 is 0, 1, 0, 1, and minus 5 is 1, 1, 0, 1, right? Let's say if we give the adder with these two numbers and then let the adder to perform additions as if it's adding two positive numbers, then 1 plus 1 is 0 and 1 carry, and including carry we have 1, we have no carry here, and 1 is 0 and carry 1, and adding these two have 0 and carry 1. By adding these two numbers and due to the overflow we miss this value, and what we have left with is 0, 0, 1, 0. This is just plus 2, right? We add 5 plus minus 5, and what we should have obtained 0 as value, but what we actually received is plus 2, which is clearly incorrect. So in this case, what the adder should have to do is, before adding two numbers, it should have checked the sign bit of the numbers, and if one of these number has the negative sign bit, then it should perform subtraction, not addition, to handle those addition. So it's more complicated than compared to just adding two numbers. Another problem with this approach is that there are two possible representations of 0. So 0, let's say if we want to represent 0 in this system, then we can use the magnitude of 0, or absolute value of 0 should be 0. And we may add 0 as sign bit, or we may add negative as sign bit of 0. That means in this system, we have two representations of 0, plus 0 and minus 0, which does make sense. So, of course, it's possible to represent 0 in two ways and regard all of these two as 0. But the thing is, if we have two possible values of 0, the problem is that when we want to check whether a value is 0, then we have to check twice. For example, if you have a program that if x is 0, then do something else, do something else. Let's say if we have such a if-else statement. This operation, this operation that is checking whether x is 0 or not, actually compare, if we have used this size magnitude number, this operation actually requires two comparisons to check if the value is 0, 0, 0, 0 or whether the value is 1, 0, 0, 0. So that is one additional complication that is using the size magnitude number. So how the numbers are actually represented in most of the digital systems, we are using a system called two's complement number to represent a negative number. So instead of just showing the formal definition of two's complement number, I'll just show you how to represent a negative number in two's complement system, and that is more intuitive to understand this two's complement number. So let's say if we want to represent -6 here, then we start by just taking the absolute value or magnitude of the value and write the value in just normal positive number format. And here we use all n bits, not just n-1 bits, from 0 to n-1. So after representing the number in positive value, representing the magnitude value in positive integer, we flip all bits. Flipping means all zeros should now become 1, and all zeros now become 1. All ones now become 0. So when we are representing 6, the value should be 0, 0, 0, 0, 0, 1, 1, 0. After flipping all the bits is 1, 1, 1, 1, 1, 0, 0, 1. After flipping all bits, the step 2 is add 1 to this value. By adding 1 to this split value, what we have is, by adding 1, we have 0, we go carry, and 1, 0. So what we have is this value, 1, 1, 1, 1, 1, 1, 0, 1, 0. This is -6 in two's complement number. So when you are using the two's complement number system, what you have to remember is actually three things. First, take the absolute value of the negative integer and represent them in just normal positive integer. And then flip all the bits and then just add 1. That is how you represent the negative integer using the two's complement number system. So what is the benefit of using the two's complement system? We can use the same addition operation, same rule, that is adding two positive numbers to add any number regardless of whether the number is positive or negative. For example, let's look at the same example here. So we are trying to add 5 plus -5. Let's represent -5 using two's complement system first. The absolute value of -5 is 5, so it's represented in 0, 1, 0, 1. And step 1 is flipping all the bits, and then by adding 1, we have -5 in two's complement system. So let's add +5 and -5. So let's add +5 and -5 in two's complement system. If we add these two, we have 0 and carry 1, and if we add these 3, we have 0 and 1 carry, and after adding these two, we have 0 and another carry. After adding these two, we have 0 and carry 1. If we ignore this overflowed carry, what we have left is 0, 0, 0, 0. As we expected, we get correct value by the result of adding two numbers, regardless of the number is positive or negative. And that is the biggest benefit of using two's complement system. So when we are adding two numbers in binary format, you don't have to carry whether the number is positive or negative. You can just add these two, just as if you are adding two positive numbers, and you are still getting the correct value. There are another benefits of using two's complement system, that is 0 is always represented by a single value, 0, 0, 0, 0, 0. 1, 0, 0, 0 is not 0 in two's complement system. That is a different number. Another slight benefit of two's complement system is we have a slightly larger range of number representation. When we have sign magnitude number system, the possible range of the number is like this one. But when we are using two's complement system, the possible range of the number is comparing with this one, we can represent one more negative number in two's complement system when we have the same number of bits. That is one possible, and there is one added benefit for using two's complement system. But anyway, the biggest benefit is we can use the same addition rule without distinguishing positive or negative numbers. You can just add those numbers as if we are adding two positive values, and we are still getting the correct value. Okay, that is the basics of the integer number system in digital systems. And in the main lecture, the computer architecture class, we'll also study the floating point number system that represent real numbers. That means the numbers that has fractional points below the decimal point. Anyway, let's move on to the next topic. Let's change the gears a little bit, and let's come back to the logic circuit again. So in digital systems, the circuits are actually made of two different parts. One is combinational circuit, and the other one is sequential circuits. Let's begin with the combinational circuits, and then we'll cover what sequential circuits later. Combinational circuits are memoryless circuits. That means it doesn't remember the previous states of the circuit. That means if we give an input to the system, then the outputs will depend on only the current input. If we change the input, then the output will change correspondingly. And there are no two different outputs coming out given the same input. And these combination circuits are composed of the combination of logic gates that we showed earlier. For example, NOT gate, AND gate, OR gate, these are possible examples of combination circuits. If we give the OR gate an input, the output will be determined just by looking at the inputs, not any other internal stage or previous history of the inputs. If we give 1, 1 to the OR gates, it always output 1. There's no case that OR gates gives us 0 when we give them 1, 1 as input. NAND gate, NOR gate is another possible combination of circuits, and we also have XOR gate or XNOR gate, and you can easily see how they operate. XOR gates outputs 1 when only one of the inputs are 1, but unlike an OR gate, input of 1, 1 also gives 0 as an output. XNOR gate is inverted version of the XOR gate. Another possible example, that is commonly used in many combinational circuits, is MUX or multiplexer. MUX selects one of the inputs as the output. So here we have AB as an input, and we have another input called selector or cell, and this selector, the role of this selector is connecting one of the inputs as the output. So if cell is 0, then the output value will be the same as A. The value of B doesn't affect the output when cell is 0. Similarly, when cell is 1, the output is just connected to input B. So input B is, let's say input B is 0 and cell is 1, then output will be 0. If the input value of B changes to 1 while we have the same cell value 1, then Z, the output, will be 1 again. The value of A doesn't affect the output when cell is 1. So you can think this multiplexer as some kind of selector that selects one of the inputs as the output. A MUX doesn't have to select an output out of these two possible inputs. There could be a multiplexer that selects the output out of multiple values beyond 2. Here we have an example of 4-input multiplexer. So we have A, B, C, D, and to select one value out of these 4 possible cases, we need 2 bits of selector inputs. So we have selector combinations as 0, 0, 1, 0, 1, 1, 0, 1, 1, and it selects one of the inputs as the output. We can always create this multiple. So when we do not have a 4-input multiplexer, then we can create one by cascading 3 2-input MUX in series. So for example, if we only have 2 input MUXes, then we can combine outputs of these 2 MUXes into one, and then we can have 4 input MUXes. And here we give them selector input bit 0, because whether 0, 1 in input bit 0 selects between A and B, and input bit 0 selects between C and D. So we give them cell 0 bit, and then the selector that selects between these two should be the selector bit 1, right? Okay, we also have the opposite of the multiplexer. We have demux gate. Demultiplexer or demux is connecting input to one of the outputs. So if we have selector value 0, 0 here, then input is connected to the first output, output A, and all the other values, in this case, are 0. If we have selector value of 1, 0, then the input is connected to C, and all the other outputs will be 0. So that's how MUX or demux works. So, like I showed you using the MUX example, these combinational gates are combined to create another functionality. So for example, let's look at how we can implement the addition system, the addition adder logic. So let's begin by just creating a 1-bit adder that adds 2 1-bit values. So here we have 2 inputs, A and B, and each of these inputs are just 1 bit. So the combination of possible input values are 0, 0, 1, 0, 1, 1, 0, 1, 1. So let's add these 2 values. So if we add 0 and 0, then the output should be 0. And if we add 0 and 1, output should be 1. If we add 1 and 0, the output should be 1. And if we add 1 and 1, let's see what happens. We have 0 as output, and we have 1 as the carry out. So we cannot just ignore the carry value, because it should be delivered to the next bit to correctly add multiple bits. So if we have 8-bit adders, then by adding the LSB, the smallest bit in the number, then the result will be the addition of those two values plus possible carry-out value, right? The carry-out value for all the other cases are 0, 0, 0. So let's look at how we can create this circuit. If we look at this summation value, the result of adding these two bits are actually the same as the XOR gate. So if we go back to XOR gate, the output is 0, 1, 1, 0. And if we just look at this summation value, this is actually the same as the XOR value. So the sum is actually represented by XOR gate that takes A and B as the input. Let's look at the carry-out value here. The value is 0, 0, 0, 1, and this is actually the AND gate, the same as the output of the AND gate. So the carry-out is simply represented by an AND gate. Right? Using this 1-bit adder, we can use this adder as for adding the LSB bits, the smallest bit, because it doesn't receive the carry from the lower bits. It only produces the carry to upper bits. But in the middle of the addition, for example, let's go back to here. In the middle of the addition, we are actually taking three values, two values plus one possible carry from the lower bit. And it also produces a sum value and another carry to the upper digit. So actually, when we want to build a full adder, we need to create an adder that takes two input bits and then one carry in bit from the lower digit, and then produces two values. One is the summation and another carry out that goes to the upper digit. So to create this circuit, then one of the possible ways to create circuit using this for such cases is that first we fully fill the truth table, and then find the combination of the logic gates that performs this operation. Actually, a large part of the digital logic design class is devoted to studying how we can create the combination of logic gates that perform such operation. But for this class, we are not asking you to create a digital logic circuit that performs certain operation. That is the focus of the digital logic class. But the computer architecture class is more focused on how the processor processes instructions or machine codes to handle user level software. So we are not going into the details of the circuit design or creating the combination of gates to give the functionality of the given function. So let's just skip this part, and you can just remember that these combination logics that produces an output given the input can be created by combining these logic gates. Okay, so if we have an adder, either it's a half adder that does not take the carry in from the lower bits, or whether it's a full adder, half adder, full adder, that also takes also receives a carry from the lower bits and produces another carry to the upper bit. We can create a full adder that adds multiple bits of that adds two integers that have multiple bits each. In this case, we are adding two 4-bit integers. So to add the lowermost bits, then we use half adder that does not take the carry in, but to add the other values, we have to use a full adder that takes in the carry value as well. This kind of adder logic that connects these carry out values in a cascaded fashion is called ripple carry adder. That means the carry propagates through the bits. Actually, this is one of the simplest implementation of the adder logic, but at the same time it's quite inefficient because the result of the lowermost bits has to propagate all the way to the uppermost bit. So there are more clever ways to design the multi-bit adders to reduce the overhead of cascaded carry bits, but also, again, we are not going into the details of the logic design here, so I'm just giving you the overview of the logic design. So if you're interested in more adder logic, then please take the full logic design class and then come back to computer architecture class. But let's move on for now. This combinational logics produces output given the input almost instantaneously. However, it's almost instantaneously and it's not directly. That means when we give the input to the combinational circuit, there are small amount of delay that to produce the output value. For example, here, if we give them the input A and B, then it takes a small amount of time to produce the output. For example, here, let's start with, so let's look at this AND gate first. At first, we have 1, 1 as the input from the both A and B. So output of G, let's start with G, output of Y. Output of Y was 1 because adding an AND operation of 1 and 1 is also 1. But let's say one of the input has changed to 0 at time 1. Then the output of this AND gate, Y, should be changed to 0 as well because one of the input to AND gate has changed to 0. But it doesn't go to 0 instantaneously like this. In this case, let's assume the delay of this AND gate is 3 nanoseconds, and the output of Y changes to 0 finally only after plus 3 nanoseconds. Similarly, let's look at this NAND gate. Previously, it's taking input from A and Y. When A was 1 and Y was 1, output of NAND gate was 0. Right? If we NAND gate, output of NAND gate is 0 when the input is both 1. Right? Input of the NAND gate, Y or A or Y, doesn't change until this time, right? So the output of the NAND gate is still 0 until this time. At this time, one of the output to this NAND gate, Y, changes to 0. But it also takes time, the time of 2 nanoseconds, to reflect the input to the output. So after another 2 nanoseconds, the output of the NAND gate, Z, changes to 1. So what this means is that combinational logic has propagation delay, although it's quite small, but the input needs to take time to become the output. Computer systems are fast, but they are not infinitely fast. And the biggest reason is that it has propagation delay. If you give the computer CPU with 2 numbers to add them, it takes time because of this propagation delay through the addition logic. If the circuit has a very long chain of combinational gates, then it takes more time to process those numbers. And that limits the performance. That is one of the factors that limits the performance of your computer system. There are many ways to deal with these propagation delays, and one of the possible way is using pipelining. And pipelining is one of the biggest topic or biggest concepts that we are going to study in the computer architecture class. And after the middle of the class, around after midterm, then we'll go into the details about the CPU architecture and how pipelining helps to solve this propagation delay to make a faster computer system. So we have studied the combination logic, and let's study the sequential logic. Combination logic only depends on the current input. The current input determines the output value. It does not affected by any other states. Sequential logic is opposite. Sequential logic is not just output of a sequential logic does not depend on the input value only. It also affected by the internal states or saved state inside the sequential element. If you are if you get confused about this explanation, a more direct or strict explanation of sequential logic is some kind of memory that saves a value, and we can use the saved value later. That is one possible way to describe a sequential element. There are many different types of sequential elements in digital logic circuits, but we are mainly dealing with only one type of sequential elements in this class, that is flip-flop. So flip-flop is saving one bit inside it, and we can use the value later. So here is the symbol that describes a flip-flop, and it takes D as input, and input will be saved internally inside the flip-flop. And then the output from the flip-flop is the saved value inside the flip-flop. So input is connected to the internal states, and the output is getting the states from the internal value. Then you may think question that what is the difference between just connecting directly the Q output? It is also getting the input, and the output will be the same value as D. The biggest difference between flip-flop and just connecting input to the output is when the value is saved to the internal state of the flip-flop and how long the saved value lasts. That is the key concepts of the flip-flop. To distinguish those timing, we need another input that is called clock input. So the clock is just a value that toggles between 1 and 0. 1, 0, 1, 0. You're familiar with clocks in computer CPUs, right? When we describe the performance of CPU, we may use how many gigahertz it has, like 3 gigahertz of CPU or 4 gigahertz of CPU. And that determines how fast this clock toggles between 1 and 0. 1 gigahertz clock means it toggles between 1 and 0 10 to the 9 times per second. So the duration of this toggle or cycle, this clock period, is 10 to the 9, 1 over 10 to the 9 seconds in 1 gigahertz clock CPU. If we have a CPU with 2 gigahertz of clock, that means the clock toggles twice as much per second compared to the 1 gigahertz clock. That means the clock period is in half for 2 gigahertz CPU. Anyway, the duration of this 1 to 0 and 1 toggle determines how long this flip-flop holds the value. The flip-flop receives the D input when the clock changes from 0 to 1. So when clock changes from 0 to 1, it's called the rising edge of the clock. The input is stored inside the flip-flop. And then the stored value lasts until the next rising edge of the clock. So let's look at the actual example here. So we have D value that is 0 here, and then it changes to 1 here, but it doesn't actually affect the output directly. The changed input that is changed to 1 is affected to output after it is saved internally to the flip-flop. So, and that happens when we have a clock toggle from 0 to 1. At this rising edge, the flip-flop stores the current value of input internally. So at this rising edge, at this time, the value of input is 1. So value of 1 is now stored inside the flip-flop. And now the Q, the output of the flip-flop, is producing 1 as output. It has a slight delay between the rising edge and until the Q, the output, produces the actual sampled value from the input, and that is actually some kind of propagation delay here. But ignoring this, what flip-flop does is at the rising edge, it samples the current value of the input, and that becomes the new current internal state of the flip-flop. And the same value will be the output of the flip-flop until the next rising edge. So during this next clock period, the output value of the flip-flop will be the same. It does not change even if the input is now become 0 again. The changed value does not get sampled by the flip-flop until the next rising edge. So the state of the input when the clock toggles from 0 to 1 matters. The value of the input during the clock period doesn't matter. It only matters when we have rising edge here. When we have another rising edge here, it samples the value again, and now we sample 0 as the input of the flip-flop, and it becomes the new value of the new output value of the flip-flop for the next clock period. So, simply speaking, the flip-flop saves the value on the rising edge of the clock period, and then the saved value does not change during the next clock period, regardless of the change of the input. Okay, in this short introductory video, we have covered very basic concepts of the digital logic circuits, and the contents that we have covered in this video is essential to study the computer architecture class. Sometimes we need more knowledge from digital logic circuit design to explain how CPU works. Then I will explain those concepts in the main lecture as well. And if you do not understand the concepts, or if you need more explanation, please don't be hesitate to ask questions. Or you can post questions through emails, iCampus, or whatever channel you'd like. So please don't be discouraged to take the computer architecture class if you didn't take the digital logic circuit design class. But if you haven't studied digital logic circuit beforehand, then I'd recommend to study the textbook, and the textbook has an appendix section that explains the same level, that also explains the very basic concepts of the digital logic design as well. So if this video wasn't enough to study the CPU architecture, then, and if you feel a little lagging behind, then you can ask questions, of course, but I'd recommend to read the textbook, the appendix section, and then you can have more concrete background knowledge about digital logic design, and your understanding about this CPU architecture will be more stronger.